Okay, now I believe all this has been posted, if I'm not mistaken. But I think this part follows what we were just doing and hasn't yet been posted. So, just looking up here at the part of the board above here and to the right of here, we have a circle, we have the polar axis, and we have a density function rho of r theta. I'm going to get rid of using rho in the near future because we could easily confuse that with a spherical coordinate. But here it means density, okay? If we set up our partition, we see that we're going to get an integral for this circle where theta goes from 0 to 2 pi and r goes from 0 to a. Fixed intervals for both a, r, and theta. And boy, I did a bonehead thing here. So just to illustrate what could happen, I left off my r in my area increment. Okay, so this really should be r dr d theta, which is going to change all my results. Okay, so I went ahead and integrated this without having the r in there. So, you know, my results are all going to change. The principle is clear enough, but I did a bad job here. Okay, I think it was the end of the class, but that's no excuse. Okay, well, having corrected this, the mass then is the integral of rho of r theta, the density, times the area increment. So here's density and area increment. I'm not going to spell out the whole word increment because of space. Okay? And so if rho of r theta is 1 plus r, what do you get? Well, there's our integral. We just plug in the density and then times the area increment. And of course, we're going to get r cubed over 3 plus r squared over 2 when we multiply this out and integrate it, and that's just trivially obvious. So that'll be a cubed over 3 plus a squared over 2. Okay, so now we've done the inner integral. And our a cubed over 3 plus a squared over 2 is just a constant, since, you know, the a is just the radius of the circle. So we can factor that out of the integral, and now we just have the integral from 0 to 2 pi of d theta. And the integral from 0 to 2 pi of d theta is just theta, and a derivative of 1 is just theta, evaluated between 0 and 2 pi, which gives us 2 pi. And then, correcting, we have an a cubed over 3 here, multiplied by the 2 pi, so we end up with 2 pi a cubed over 3 plus pi a squared. Now my corrections show you the consequences of leaving an r out. Now I didn't do that intentionally though, I just did that. Okay, so just one example of how you would do a mass integral. So this is the total mass. If I wanted to do a moment of inertia about the origin, something rotating about the origin, I'd have to put in another r squared here because I'd have to have mass times r squared, okay? Mass times the square of the distance from the axis. So I'd have another r squared in here, which would just raise the powers of r and give me higher powers of a in the end and different denominators. But it would be an equally easy integral in this case. Now, it's not always the case that it's going to be easy. You don't always have fixed limits on the integrals, but in getting used to integrals in polar coordinates, our first example really should have the simplest possible limits, and then it becomes fairly easy to adapt to other types of limits.